Isolate the exact microsecond the American Cold War armored doctrine collapsed. Let us run the simulation. Render an extreme slow-motion cross-section at 10,000 frames per second. Watch closely as a depleted uranium armor-piercing, fin-stabilized discarding sabot round, traveling at Mach 4.4, impacts a small steel box mounted on a Soviet tank. In exactly 0.003 seconds, a massive high-pressure detonation snaps this solid kinetic penetrator completely in half. This is the kinetic shatter. This is the exact mechanical failure that instantly transformed an entire fleet of 15,000 M60 Patton tanks, representing a $7.5 billion investment, into 50-ton steel coffins before the Cold War even ended. Welcome to DEFUNCT. Today, we are stripping away the propaganda to analyze the micromechanics of the most devastating technological blind spot in NATO military history. Let us peel back the homogeneous cast steel turret of the M60 Patton. Delete the outer armor plating, isolate the main armament, and zoom directly into the breech of the M68 105mm rifled gun. To understand the magnitude of this failure, we must first analyze the weapon that gave the Pentagon its false confidence. The M68 was considered a mechanical masterpiece of the 1970s. Let us simulate the firing sequence. Watch as the firing pin strikes the primer. 5.5 kilograms of M30 multi-perforated propellant ignites instantly. The internal pressure inside this steel chamber violently spikes to 50,000 pounds per square inch. To put that into perspective, that is roughly the same pressure found at the bottom of the Mariana Trench multiplied by 3. This massive thermodynamic expansion forces the M774 kinetic energy projectile down the rifled barrel. Zoom closer into the rifling grooves of the M68 gun tube. There are exactly 28 right-hand twist rifling grooves machined into the chrome-plated bore. As the round is violently forced through this 105mm tube, the nylon obturator band engages the rifling, imparting a spin rate of roughly 1,000 revolutions per minute. This spin ensures the aluminum sabot petals discard simultaneously upon exiting the muzzle. Render the muzzle blast. The superheated propellant gases, expanding at over 3,000 degrees Celsius, erupt into the atmosphere. Isolate the projectile in midair. Notice the aerodynamic design. The sabot petals separate cleanly due to centrifugal force and air resistance. What remains is a monolithic penetrator dart composed of depleted uranium, a material 1.6 times denser than lead. This heavy metal spear is now traveling at 1,500 meters per second. This kinetic energy is absolute. The Western armored doctrine relied entirely on this brute force mathematical equation, where mass times velocity squared equals armor penetration. The data proved that this depleted uranium dart possessed enough kinetic energy to punch cleanly through 350 millimeters of rolled homogeneous armor, steel, at 2,000 meters. Let us analyze its metallurgical composition. Depleted uranium, alloyed with 0.75% titanium, exhibits a unique physical property called adiabatic shear banding. Unlike tungsten, which tends to mushroom and blunt upon impacting heavy steel armor, depleted uranium self-sharpens. When the nose of the dart strikes a steel plate, the edges of the impact zone shear away, maintaining a continuous razor-sharp point that burrows deeper into the target. This pyrophoric material also combusts violently upon penetrating the crew compartment, turning the interior of an enemy tank into a superheated vacuum of vaporized metal and flame. American engineers calculated that this raw kinetic output was more than enough to tear through the sloped frontal glacis of any early-generation Soviet tank. Before we initiate the impact sequence, let us briefly examine the defensive architecture of the M60 Patton itself to understand the NATO mindset. Rotate the 3D model 180 degrees. Highlight the frontal hull glacis. The M60 relies on conventional passive protection. It is a massive block of cast homogeneous steel, measuring 155 millimeters in thickness, angled at 65 degrees. This gives it an effective line of sight thickness of roughly 250 millimeters. It is a static, rigid wall of iron. It absorbs kinetic energy purely through material density. If an incoming projectile possesses more kinetic energy than the yield strength of this cast steel, the armor fails. It is a binary equation. The American designers assumed the Soviets were utilizing this exact same passive, monolithic armor philosophy. They assumed the T-72 was simply a thicker wall of steel. This fundamental misunderstanding of Soviet material science is what condemned the M60. The Soviets had abandoned purely passive steel blocks. They had embraced dynamic, active physics. They designed an armor system that did not just sit there and take the hit, but violently exploded back against the attacker. Shift the environmental rendering engine to a simulated full-to-gap battlefield. Place our M60 Patton at a standoff distance of 1,500 meters from a Soviet T-72 main battle tank. Execute a wireframe transition on the T-72's frontal glacis. Isolate the small, rectangular boxes bolted to the hull. This is Kontakt-1. To the American intelligence apparatus, these looked like spaced armor blocks or auxiliary storage. In reality, this was explosive, reactive armor. Let us make the outer steel casing of one Kontakt-1 brick completely transparent. Look inside. You are looking at the 4S20 explosive cell. It is elegantly, terrifyingly simple. 2 flat steel plates, each exactly 3 millimeters thick. Sandwiched between them is a precisely measured 260-gram layer of PVV-5A plastic explosive. This is not a passive wall. This is a mechanical trap designed specifically to break the laws of kinetic energy. Resume the simulation at 10,000 frames per second. The 105mm depleted uranium dart approaches the target at Mach 4.4. The razor-sharp tip of the penetrator makes physical contact with the 3mm outer steel plate of the Kontakt-1 brick. At this exact microsecond, the friction and immense pressure of the impact generate a localized temperature spike exceeding 3,000 degrees Celsius. This thermal shockwave instantly detonates the PVV-5A plastic explosive layer. Freeze the simulation. Analyze the detonation vectors. The high explosive charge does not blow outward in a random sphere. The blast wave propagates parallel to the steel plates at a terrifying velocity of 7,500 meters per second. This confined detonation generates a localized overpressure of 300,000 pounds per square inch. This pressure violently accelerates the 2 3mm steel plates in opposite directions. The outer plate is blown outward toward the incoming dart, while the inner plate is driven backward against the tank's main armor to bounce back. Now, advance the simulation frame by single frame. Observe the kinetic shearing phenomenon. The American depleted uranium penetrator is long, thin, and optimized strictly for forward penetration. It possesses incredible compressive strength, meaning it can withstand immense pressure, pushing head-on against its tip. However, it is structurally vulnerable to lateral shear forces, meaning pressure, applied directly from the side. As the dart attempts to push through the exploding Kontakt-1 brick, the heavy steel plates are moving rapidly across its flight path. The outer plate strikes the side of the ultra-dense dart at roughly 500 meters per second. This lateral impact applies a massive shear stress to the crystalline structure of the depleted uranium. The mathematical equation of the M68 cannon completely falls apart right here. The moving steel plate creates a guillotine effect. It introduces an extreme yaw angle, forcing the tail of the dart to swing violently off its central axis. Depleted uranium is dense, but it is also brittle under extreme sideways torque. Watch the material failure unfold. The immense lateral kinetic energy snaps the monolithic penetrator clean in half. The solid spear of heavy metal fractures into multiple jagged, useless fragments. What happens next is the death knell of the M60 Patton. The shattered fragments of the dart finally impact the main cast steel armor of the T-72. But because the penetrator is no longer a single, unified mass traveling on a perfectly straight axis, its kinetic energy is entirely dispersed. Instead of a hyper-concentrated point driving 350 millimeters deep, the broken pieces merely gouge the surface paint and shatter harmlessly against the Soviet hull. The penetration value drops from over 300 millimeters to less than 50. The most advanced kinetic energy round in the NATO arsenal has been completely neutralized by 260 grams of plastic explosive and 2 thin sheets of steel. Pull the camera back to a macro view of the battlefield. The implication of this micro-mechanical failure is absolute devastation. The United States military had built its entire European defense strategy around a fleet of 15,000 M60 Patton tanks. That is a $7.5 billion investment. Every single one of those machines, with their massive 155mm cast steel turrets, their complex hydraulic traverse systems, and their massive Continental V12 diesel engines, were instantly rendered obsolete. They could not kill the enemy they were designed to fight. If the Cold War had gone hot in the mid-1980s, the M60 fleet would have been systematically slaughtered in the Fulda Gap. Their passive armor would have been effortlessly pierced by Soviet 125mm smoothbore guns, while their own returned fire would have shattered harmlessly against the Kontakt-1 bricks. This catastrophic engineering blind spot triggered absolute panic within the Pentagon, forcing the rushed development of the 120mm smoothbore cannon and the M1 Abrams to regain the kinetic overmatch. The M60 Patton was not defeated by a bigger gun or thicker armor. It was defeated by the fundamental misunderstanding of active material science. It was defeated by a cheap, exploding brick. If you want to continue stripping away the propaganda to analyze the fatal mechanical flaws of military history, do not forget to subscribe to DEFUNCT. Leave a comment below on which obsolete titan we should dissect next.